I'm Terry Powell, the Community Relations Officer at Berkeley Lab, and I'd like to welcome you to Berkeley Lab Friends of Science sponsored talk tonight, Science at the Theater. I thank you for your interest in the scientific research being done at Berkeley Lab. And I thank our many co-sponsors for these talks, including the UC Berkeley Chabot Space and Science Center, the Exploratorium, the Osher Lifelong Learning Institute at Berkeley, Lawrence Hall of Science, and especially our science departments in our local high schools, Albany, Berkeley, and Ozone. Our speaker tonight is Bill Collins, a UC Berkeley professor in Earth and Planetary Sciences and a climate scientist at Lawrence Berkeley National Lab's Earth Sciences Division. As this talk's announcement identified, Bill Collins headed the development of one of the leading climate models used in national and international studies of global warming. He now directs the lab's research dedicated to atmospheric and climate science. What the announcement did not say, because the information wasn't yet available, is that Bill Collins, a lead author of the most recent assessment of the science of climate change by the United Nations Intergovernmental Panel on Climate Change, shared the 2007 Nobel Peace Prize with his many fellow climate change scientists and, of course, former Vice President Al Gore. Setting out to be an astrophysicist, Bill Collins earned his BA in physics from Princeton University, and in 1988 his PhD in astronomy and astrophysics from the University of Chicago. However, attracted to problems that evolved on a shorter time scale than that of the cosmos, he focused his interest in climate science research during 4 years at Scripps Institute of Oceanography, beginning with studies of clouds and their effect on Earth's radiation budget. We'll learn more about that tonight. He then spent the next 10 years at the National Center for Atmospheric Research in Boulder, Colorado, where he led development of the third iteration of the powerful Community Climate Systems Model, sponsored by the National Science Foundation and the Department of Energy. He arrived in Berkeley this past April, eager to accept the challenge of reducing our carbon footprint with frontiers in climate forecasting, the subject of his talk tonight. Please welcome Bill Collins.
It's a real honor to be here, and hopefully, I usually make very snide remarks about Windows machines, but my Mac has been acting up, so we'll have to hope that it cooperates this evening. Anyway, it's a real pleasure to be here and to have joined the Berkeley community. My wife and I moved here in April of this year from Boulder, Colorado, and our goal in moving here was partly to enjoy the Bay Area, but also because there are tremendous opportunities at Berkeley and Lawrence Berkeley to move beyond the issue of ivory tower science and the pursuit of science's sake, which is what I've been doing for most of my career, and to begin to connect that science directly to action to save the environment. And I'll talk to you a little bit about that action later on in my talk. So here goes. Yes, okay, good. My Mac is cooperating. So I wanted to talk to you about some central questions in the whole field of climate change, and questions that we've been trying to address over the last 30 years or so. I'll start by describing what is climate, and actually that's a question to which we really still don't have a precise answer, but I'll give you a working answer so that we can define and distinguish climate from weather for the purposes of this talk. And then talk about how climate is changing now. This is sort of a key fact. Climate change is literally now occurring before our eyes. It's occurring so rapidly that we can see it within a single human lifetime. And I'll show you some evidence for how climate has recently changed and why we think that's compelling evidence for the fact that it will continue to change in the future. Of course, then a central question is what causes these changes? Could it be natural? Could it be man-made? And I'll attempt to address that question and provide you with what I think is science's most definitive answer yet, that these causes are man-made in the recent past. And here's the part of the talk that I imagine you all came to see, which is what could happen next. And I'll spend a little bit of time on that. But I don't want to dwell on it. It actually, this is, if I had given this talk a little bit closer to Christmas, I would have sort of oriented it around Charles Dickens' Christmas Tale, which is, by the third act, the third ghost, Dickens is very depressed about what will happen in the future, and then the story ends in a happy ending. And actually, I am an optimist at heart, so I do want to end on a happy ending, because I think there can be one. So I'll conclude with what we can do to avoid warming, and show you a concrete example of how we have addressed climate change in the past internationally. And so I think there's actually excellent precedent for addressing these kind of problems. So let's start with the issue of what is climate. And I want to distinguish this from weather. So weather refers to current atmospheric conditions at a particular place in time. So I'm showing you a movie loop here of clouds evolving over the Earth's surface. This is data taken from modern satellite instruments, and it's showing you the weather literally as it evolves hour to hour. Climate refers to the general weather patterns that apply in a particular area. And this is a map, which it may be hard for you to read, showing you the average cloud amount over the Earth's surface in October, so this month. Areas which are white, for example, down here in the southern hemisphere, are completely socked in with cloud. And you can also see the storm tracks in the northern hemisphere, and then some of the major cloud systems over the tropics. This is what we mean by climate. It's basically a condition that applies on average to any particular place. And climate can evolve in time. So the climate in the United States, for example, has evolved considerably over geologic time. We rely on the stability of climate. And what I'm showing you now is a movie loop indicating how trees and plants orient themselves around the climate in the United States. Climate in the United States and in North America sort of follows a gradient in temperature. And so you have climate zones in Central America that are appropriate for tropical conditions. And then as you go further north, you can see these sort of trend over into Arctic conditions. And depending on altitude, for example, in the Rockies, you can also go into alpine conditions. And this is an area that Jen and I lived in up until April of this year. So you can also have gradients at the same latitude, but just going in altitude. Mankind has relied on the stability of climate zones for all of its recorded history. And just to show you an example of that, here's a wine region in southern France, which has been used for cultivation literally since Roman times. And we have historical records going back well into medieval times, but also evidence from Roman times that people have been cultivating this area and certainly using it for wine manufacture for several centuries at least. So there are Roman ruins in this photograph taken from this region, and evidence also from the 19th century that it was used extensively for wine. This is a painting by Van Gogh. So we've relied on the stability of climate in order to set up our cities, our agriculture, and most of our social infrastructure. And the question that we should now ask ourselves is what happens if these climate zones begin to change rapidly with time? What will happen to our ability to farm, for example, if a region gets much hotter or much drier? And that actually is a prospect that we face this century. It's really going to happen in some of our lifetimes. So these key questions really are, what changes have occurred in the past? What is happening now, and what changes lie ahead? And this is sort of a cartoon of the climate system. This shows you the complexity of the system that we're trying to analyze. And we've been able to capture this through a combination of basic theory, a lot of observational work, and then simulation on computers to try to represent this system. The aspects of climate that make it challenging and that distinguish it from the weather that you see on the evening news are that there are parts of the climate system that take a long time to change. And the ocean, for example, is a part of the climate system that takes a long time to change. The ocean, the way the climate scientists think of it, at least scientists like myself who focus mostly on the atmosphere, so we have a very atmosphere sort of centric focus on the world. We view the ocean as a 4.5 kilometer deep bathtub, which means it has a very long time to change its temperature. In other words, what we call a very large thermal inertia. And it takes about 1,000 years for the ocean to completely mix. So it's a very long-lived, slow part of the climate system that responds on much slower time scales than the atmosphere can, for example. Another part of the climate system that responds relatively slowly is ice on land. Glaciers take centuries to change, although we now have evidence that they're changing quite rapidly. So our challenge in representing the climate system is to understand the relationship between all these different moving parts, and then to relate observations about how climate has changed in the past or in the present day to how the system might be changing, and then use that understanding to project the future. So let's talk a little bit about how we understand the climate system. It's challenging because in the present day, of course, we have marvelous instruments, probably more data really than we can hope to understand, from a variety of sensors, and I'll show you some examples of those in just a moment. When we go into the past, we don't have human instruments, and we don't have human records really that are adequate once we go past the beginning of recorded human history about 5,000 years ago. So we have to use other lines of evidence to figure out what's happened in the climate. And of course, there are excellent records that nature has constructed for us in the form of fossils. This is some of the earliest records that were used to reconstruct the past. Ice cores, which I'll come back to in a moment. This is one of the key climate records. Tree rings, which go back several thousand years, and we can use to look at drought situations. And pollen. Pollen is an interesting one because if you find pollen from ferns, for example, in an alpine climate, that tells you that that alpine climate at one time was much warmer, or most likely much warmer. And so pollen is actually a very good indicator of whether or not you were living in a wetter, warmer climate or a cooler and drier climate in the past. So these records provide us with a means of going into the past, understanding the present. To go into the future, we still don't have time machines, and so we have to have some other way of figuring out what might happen in the future. And we do what any good physicist does, which is to assume that the laws that apply to the present day are general. And if we build those into a mathematical model and then put it on a computer, the same physical laws should apply in the future. And we've made that leap of faith. It actually works very well in physics to build advanced computer models that we can use to project the future. And so I'm going to show you evidence from all three different kinds of climate records in this talk to indicate how the climate has changed in the past, to relate that change to even deeper time, and then in the middle of my talk, use a climate model to go forward in time. So this is a little bit more discussion with regards to the records that we have of the past. The ice core records are really key for this discussion, and you might ask why. What is it about ice that's useful? Most of these records are coming from deep glaciers. These are glaciers, for example, over Greenland and Antarctica, which are hundreds of thousands of years old. And when the snow is laid down on those glaciers, bubbles of air are trapped. And those bubbles contain the atmosphere from when that snow was formed. And so if we take literally take a core sample out of the ice and then melt it and extract the air from those bubbles, we can look at the chemical composition of the Earth's atmosphere going back hundreds of thousands of years. And that's a critical record for understanding how the Earth's climate has varied literally over the last million years. Perhaps the critical climate record. Tree rings work over much shorter time scales, and then of course we do have evidence from the last few thousand years about when trees flower, and also from harvest production. Some of these coming from human records, dating all the way back to Mesopotamia in the Middle East. In the present day, we're blessed with a huge variety of observations. Some of the first measurements were made with balloons. So you stick an instrument package on the bottom of a balloon, you launch it, that balloon flies up into the atmosphere, and it provides you with sort of a vertical record of the temperature and humidity in the Earth's atmosphere. And these measurements date all the way back to the Second World War. So we have about 50 years of balloon measurements. Around the same time, people realized that they could instrument aircraft to make measurements of the Earth's atmosphere. And we now are using modern aircraft. This is an aircraft that was just recently purchased by the National Center for Atmospheric Research in Boulder. It's an executive Gulfstream 5, where they've ripped out all the nice leather seating and replaced it with very hard seating and a lot of instrument racks. But this is an excellent plane for making measurements of the atmosphere. It can fly up to 50,000 feet and can make measurements over several thousand square miles. When you want to place the measurements from balloons and aircraft into a context, maybe a global context, we now have satellites. And I'll show you some data from satellites in just a moment regarding sea ice. These literally provide a global view of how the climate is changing, although our records from these are relatively short, only about 25 years or so. So here's our crystal ball, climate models. These are the things I've been working on for the last 7 years or so. And this is a simulation of sea surface temperature a little bit in the future from one of these models. What are these models? They're literally just a set of equations that describe the basic fluid mechanics of the Earth's atmosphere, conservation of mass, the basic laws of thermodynamics, physical laws that we were all taught in school, combined with some aspects of the climate that we're still doing research on. So these models are not sort of finished and done yet. We're still doing a lot of research to understand aspects of the climate system that are not well represented in them. But they do represent a synthesis of what we know about the climate now. And we can use them to go into the past, to try and understand what happened in the past when we, for example, have incomplete instrumental records. We certainly can use them to project the future. And I'll show you an interesting example where we can use them to generate sort of a parallel Earth, an Earth without people. And that turns out to be a critical experiment for understanding what has been causing climate change in the recent Earth's history. As Terry mentioned, there's been a recent assessment of much of this scientific activity that's now available through your favorite local bookseller or online bookseller. The first report, The Physical Basis of Climate Change, is now on the bookshelves. And as Terry mentioned, it was just recently awarded the IPCC. The IPCC was awarded the Nobel Prize for its contributions to understanding climate change and its implications for world affairs. This report is actually the first of three. So the report that I worked on deals with the science. There's a second report, which will be issued soon, which looks at the impacts of the science for human society. How will human society be affected by climate change? And then the third report deals with options to slow or halt climate change. And that's really quite a critical report for us as we move forward. I will be primarily focusing on the state of the science, although I'll touch on these other issues a little bit in my talk, because this is the report that is now out and available, and it's also the area with which I've had the most contact. I will say, though, just sort of in passing, that the third report is quite optimistic, that there are good options that are affordable for us to make significant cuts in our greenhouse gases, and based on technology that's available now or will be available in the very near future. What I'm going to show you are a number of slides, but basically 7 key figures that came out of this first report. And the thing I want you to understand about this report is that it is an assessment of the science, which represents not only the scientists' opinions, but it was also signed off by all the member states in the United Nations, including major oil producers like Saudi Arabia, major coal burners like China and the United States. Every single country that is a member of the United Nations General Assembly signed off on this report. Literally, they debated it line by line, adjective by adjective, figure by figure. So what I'm going to show you is not only the consensus of the scientific community, but the consensus of the scientific community that's been blessed by governments, by companies, by non-governmental organizations, and by climate skeptics. The other aspect of this report I want you to realize is that we opened it up for comment, literally to the worldwide scientific community. We had about 30,000 comments on this first report, which we had to answer. We had to answer all of them. This is our homework. And all of that material will be in the public domain very soon. So if you're interested in going through and seeing how we responded to the climate skeptics, I invite you to do so. The spreadsheets will be available in the not too distant future. It might make it the interesting material for a few PhD dissertations. But the point of this is to indicate to you that this is really truly a global consensus about the state of the science. So let's start with evidence for recent climate change. What I'm showing you is evidence that would be visible to anyone who had lived before the Second World War and gone to Glacier National Park. This is a park that's in Montana. I went there in the 80s, and I urge you, those of you who have young children who want to go, you should go soon. because these glaciers are disappearing at a rapid clip. This is one of those glaciers just before the Second World War, and you can see how the glacier backs up against this rock wall. This is the state of the glacier today. It's melted. It's lying in chunks in a lake formed at the bottom of this cliff face. This has happened in just about 70 years, so just under one human lifetime. So the evidence for climate change is now visible to the naked eye. This is one of the key findings from the IPCC report. So I'm going to show you 7 figures. This is the first of 7. What this is showing you are the changes in temperature, and these are all unfortunately, all of these graphs are in metric, so I'll do the translation for you. And the other thing to realize is that many of these are expressed in terms of a change relative to the past. So this is the change in temperature. This is not the absolute Earth temperature. It's the change in temperature that has occurred over the last 150 years. The point of this graph is that the temperature has risen by about 1.5 degrees Fahrenheit since the start of industrialization in the 19th century. Sea level has been climbing steadily. And by the way, we're fortunate that there were measurements made from ships, people dropping buckets into the ocean as they sailed around the world. It took crude thermometer measurements and accumulated all that data, and that's how we know the change in the temperature. With sea level rise, they made tidal measurements and used tidal gauges, again dating back to the middle of the 19th century. The record is now being constructed almost entirely by satellite, but it's a continuous record, and it suggests that sea level has risen by 10 inches, close to a foot, in the last 150 years. And snow cover on land has decreased steadily over the last century or so. And there's been a dramatic increase in the rate of change since the 1970s. So again, evidence for change in the climate. We're not necessarily saying this is man-made, but the climate is changing, and it's changing rapidly. There is evidence for rapid change if you look at sea ice. So this is one of those places where we really didn't have adequate data until the advent of satellites. The satellite record only goes back to the late 1970s. This is Arctic sea ice taken from satellites really at the start of the satellite record, 1979. This is the extent of the sea ice 2 years ago. You can tell by eye that it shrunk quite a bit. If you actually look at the area of ice over the Arctic basin in the northern hemisphere, it's decreasing at a rate of about 7.5% per decade. So let's just assume that this trend applies for the next 100 years. That's a 75% decrease in sea ice extent over the next century based on the current trend. And I'll show you projections for this a little bit later in my talk. So quite dramatic changes in the Arctic. And this is a figure that just appeared in a recent article in Science. This white area is the extent of ice this year. This dotted line is really the line I want you to focus on. This dotted line corresponds to an area that was always covered by sea ice up until this year. In other words, this year-round, there was ice inside this dotted perimeter. This year, for the first time, we've broken inside that perimeter. And so the sea ice has declined dramatically compared to the previous satellite record. Greenland is melting rapidly. We have a lot of evidence for this. This shows you the area that's now melting actively, and this is from a couple of years ago. And moreover, there's evidence as they make measurements that this perimeter where the melt is occurring is moving inward. And so here's some evidence from 2 years ago that melt for the first time was recorded. So the melting line, the line of ice that's melting, is encroaching on the center of Greenland. We're now able to measure from satellites, by looking at the gravity of Greenland, how much water it's losing every year. And it's losing about 250 cubic kilometers of water every year. Now, I'll do the translation for you. That's about a cube of water 4 miles on a side that it's losing every year now. And there's other evidence that Greenland is changing rapidly. You can look at earthquakes generated by the Greenland ice sheet. It shakes as it moves, and actually a lot of this, the change that I'm talking about is not necessarily melting, it's actually just the ice flowing into the sea. And that rapid motion is generating quakes that have doubled in their intensity in the last 5 years or so. So again, quite strong evidence that Greenland is changing rapidly right under our noses. And another line of evidence in this regard are changes in areas that are built on permafrost. So this is what's known as a drunken forest from Alaska. This is one of the reasons why Alaskans, including some of its more conservative members in Congress, are now convinced that there is climate change because the trees that are rooted in permafrost can no longer stand up straight. Their roots are embedded in a layer of frozen soil that's melted, so the trees are tilting over. Alaska is actually not the most dramatic example of this. There are villages where they're literally falling into potholes that are football field in size. And so many parts of Russia are now being affected by severe permafrost melt. So they have very direct evidence that the permafrost is melting out from underneath them because their villages are disappearing into these huge sinkholes. So that's the evidence for recent climate change. Let's talk about why it's happening. And I'll just talk about this briefly to introduce the subject, the physics behind climate change. The main issue is that the Earth has an energy balance, kind of like an economic system. It has an input and an output. The input is sunlight. The output is infrared radiation. This is in wavelengths that I can't see. It's basically heat being emitted to space. And under normal circumstances, the sunlight and the heat balance each other. And that results in a balance in the climate. So if you have a balance in energy, you have a balance in the climate, and the climate remains more or less in steady state. We now have direct evidence from space that the climate is out of balance and that there's an imbalance in the Earth's energy system. Now you might ask, how can these imbalances occur? Well, one source of the imbalance can come from natural causes. So this is a photograph of Mount Pinatubo, and I'll show you what volcanoes do to the climate system in a moment. And the sun can also change. And this is a movie taken from a remarkable satellite called SOHO, which is parked in a point between the Earth and the Moon where it can stare at the sun continuously and monitor how the sun changes. And I'll come back to the sun in just a moment. So there's several major causes, natural causes for climate change that are responsible for much of the change that we see in the climate record. So if you go to the Grand Canyon and you look down the rock wall, which goes back, and the rock wall itself expresses about 600 million years of climate change, but there are rocks that go back over 1 billion years in parts of the Grand Canyon. That climate change is due to natural causes. And what scientists are asking you to believe is that for the first time ever, something other than a natural cause is responsible for the climate change that we're observing. Now, the only way we were able to prove that case to you is by analyzing these natural causes fairly carefully. So let's start with volcanoes. Mount Pinatubo went off and injected particles into the stratosphere, and I'll go back and show you this movie again, but they flood the stratosphere with particles that reflect sunlight back to space. So this one volcano completely filled the stratosphere in 1981. And let's hope in the movie, when it comes back, 1991. Let's see if the movie my Mac will cooperate here. Yeah, so Pinatubo goes off, and we flood the stratosphere with aerosols. This is the reflection of sunlight back to space just before Pinatubo, and what you're looking at is the blue color reflected by the Earth's atmosphere, what's known as Rayleigh scattering. Immediately afterward, the whole atmosphere has been turned yellow because of the scattering of sunlight off of sulfate particles, which tend to scatter in yellow wavelengths. So volcanoes can literally reduce the amount of sunlight coming into the Earth's climate, and we have direct evidence from Pinatubo that they cool the Earth's climate, in this case appreciably, by about 1/3 of a degree Kelvin. The sun can also change, and what I just showed you was the start and now the end of our record. We are fortunate to have 400 years of sunspot data, starting from Galileo, who was the first man to realize that the sun wasn't a perfect sphere. And he drew the spots on the sun's surface. And this was actually sort of a hanging offense back then. We now have modern satellite data that can show the evolution of these sunspots as they march across the sun. Now, it turns out that this activity, this is a reflection of magnetic activity in the sun, And if you count sunspots, you can relate it to the amount of sunlight the sun gives off. So let's go back to 1600 with Galileo and his intrepid measurements back then. Shortly after he started making them, there was a period when the sun went very quiet. There were very few sunspots on the sun's surface, and the sun picked up activity again. We know that this period corresponded to sort of a miniature ice age in Europe called the modern minimum, and there are paintings from that time that show how cold it got. This is our estimate in units that only a scientist could love of the amount of sunlight reaching the Earth. The point of this graph, I don't want you to worry about the units, but the point of this is that this only represents about a 0.1%, a tenth of a percent fluctuation in the solar output. So this is most of the solar variation that we're talking about in the last 400 years. And people who've claimed that the sun are responsible for the recent climate change have to somehow explain that on the basis of a tenth of a percent fluctuation in solar output. So those are the natural causes. Let's talk about the man-made causes now. Obviously, there's a lot of carbon dioxide given off by industry, by transportation, and by fires. The other thing that fires do is they introduce aerosols, like the volcanoes. They introduce aerosols into the Earth's atmosphere. For example, smoke. Smoke can reflect sunlight back to space, and you might think, well, these are just local fires. How could they possibly influence climate? There are parts of Africa that are being burned at such a rate that, this is one of the pictures that's not going to work for me. This picture showed the, I'm sorry about this. This picture showed Africa with satellite measurements of where fires were going off, and it literally blankets the entire Congo. So you can change climate in the area around Africa pretty easily just by the burning forests to prepare them for agriculture. This is, let's see if this is another slide which is not going to work, so let's not worry about the text. The greenhouse effect is what's responsible for making the Earth habitable, and what we're doing by introducing carbon dioxide into the Earth's atmosphere is altering the greenhouse effect. So the Earth and the Moon get almost exactly the same amount of sunlight. The Earth is habitable, the Moon isn't. And if you look at the Moon's mean temperature, it's well below the freezing point for water. And the Earth is above the freezing point for water, and that's obviously a critical distinction for life. The reason is that the Earth has had a natural greenhouse effect for most of its history. And what we're doing by adding carbon dioxide is adding to that greenhouse effect. So let's look at our estimates for what's happened and why that's happening. Go back one slide. Okay, good. The reason why the greenhouse effect is increasing is that we've been adding carbon dioxide. This is a time series, and remember I told you about ice cores and how we could use those to probe the Earth's atmosphere going back in time. This is an ice core record going back 10,000 years, and this is 1/100th of the ice core record. Just to put this in context, we think that man started forming agrarian society. At this time, human recorded history started about 5,000 years ago, and the industrial age is literally this spike on the graph. So over over all of human recorded history, and going back to the formation of agrarian society, the amount of carbon dioxide in the Earth's atmosphere, expressed in parts per million, was essentially constant. And then in the recent past, it increased very rapidly. And if you blow up this last 200 years, you can see it's been increasing at a steady clip. And the rate really picked up right around the time we started burning coal. Now we can prove, this is an interesting association with the industrial age. We can prove more or less, when I use the word prove, I almost mean that literally, prove that this carbon dioxide increase is man-made. You actually can't explain it from natural causes based on chemical fingerprints in the Earth's atmosphere. So the only way that reputable scientists know how to explain this increase is by attributing it to fossil fuel combustion. There's no other explanation. So I mentioned we were changing the energy balance of the Earth. This is how scientists look at this. This is another one of these key findings from the IPCC report. Let me explain to you what we're looking at. This is the change in the Earth's energy balance in units of a watt per meter squared. Now, what is that? 1 watt is about the energy consumption of a Christmas tree light bulb, and 1 meter squared is about 1 square yard. So this is the scale on this graph. One plus or minus 1 on this corresponds to adding or subtracting a Christmas tree light bulb per square yard of the Earth's surface. And what we have plotted on here are how we think the energy budget of the Earth has changed since the start of industrialization. And there's a big piece of this that's attributed to man, that's what the word anthropogenic means, and then there's a small piece that's attributed to natural causes. All the addition of greenhouse gases to the Earth's atmosphere have heated or added to the amount of energy trapped in the climate system. Then there's some effects of aerosols that have reduced the amount of energy absorbed by reflecting sunlight back to space. If you add all of these up, what you get is the net forcing of the climate system by man. Actually, and this figure includes the sun as well. And we're now quite confident, for the first time in this report, we actually say that we're more than 90% confident that we've added energy to the climate system since the start of industrialization, despite the large uncertainties in our estimates. So this would naturally lead to a warming of the climate. And now the question we want to ask is, let's go back and try to attribute recent climate change to man or to nature. So we're now going to use a computer model to try to sort this issue out. We're going to take one model and remove the humans from it and just look at the natural causes of climate change, volcanoes and the sun. So this is supposed to be our computer model representing, beautiful natural earth, rivers, people's, beaches without people, mountains without mountain climbers. And now we switch to the earth with people. So we run another computer experiment where we put in all the people. This is lights from Earth. So this shows you the sunlight that's measured, you can measure from space using military satellites. So you can obviously see the industrialized areas and the gas flares in Saudi Arabia, major urban areas all over the world, Japan. Let's compare these two simulations with and without people. And the reason we have to do it this way is that nature, unfortunately, we don't have a parallel Earth where we can run this experiment, unlike science fiction. So the only way we can run this experiment is either by comparing the Earth in the present day to the past, when there weren't people, or by doing this in a computer. And I'm going to show you the results from running this experiment in a computer. And again, what we're looking at is the change in the Earth's temperature since the beginning of the 20th century. So this is the increase relative to a baseline, an increase of about 3/4 of a degree centigrade or about 1.5 degrees Fahrenheit. And the data for the whole globe is shown in black. For land is shown in, again, shown in black in this middle graph. And then for the oceans only is shown in black on this bottom graph. And then we have two sets of simulations. The Earth, including people, which is shown in this sort of pink or salmon color. And then our experiment where we left the people out, shown in blue. And no matter where you look, whether you look at the whole globe, just over land, just over ocean, you cannot explain the recent increase in temperature if you only have natural causes. It fails spectacularly, and it doesn't matter. You can break this down even to the level of the continents, break it down to regions in the United States, you get exactly the same result. The last 30 years or so, you cannot explain unless you invoke human causes. And this is a period now where we have excellent data about what the volcanoes and the sun have been doing. So this is not because we don't understand how those natural radiative forcings have influenced the climate. This is a period where we have excellent observations of the sun and volcanoes. So we're now willing to make a statement that we're more than 90% sure that mankind has been the cause of recent climate change. So if you hear somebody say that it's debatable, and I just read a statement by a candidate from Colorado who's running for president, whom I won't name, who said it's debatable. I guess the question is debatable to what extent? And we're saying there's less than 10% chance this can be natural. So debatable by whom and on what grounds? So now let's go to the future. And this is going to be sort of the darkness before the dawn phase of my talk, I must confess. Because I think that the way I normally phrase this is that this represents a significant challenge to humanity. It is one that I think we can tackle, but it is a challenge. And you've seen a lot of figures. This is another one of these key findings from the IPCC report. You've probably gotten the flavor now that we've tended to average everything up and look at it globally. And I'll show you a map in a moment, but let me start with the globe. These are projections of how the concentration of carbon dioxide might change in the future. As a physical scientist, I really can't make socioeconomic projections, so I'm not qualified to guess how many people there'll be on the planet at the year 2100, or how much fuel they'll be consuming. We had professional socioeconomists put the scenarios together for us, and then we sort of just ran them all and didn't put value judgments on them. We just ran them through our computer models, and we've provided these projections back to our political management so they can make a decision about which outcome they prefer. Which hopefully what we all prefer. So we ran simulations where we fixed CO2 at its current concentration, and the point of this is to show that the climate system, because of this inertia I mentioned earlier, even if we were to go to a totally green economy right this minute, completely carbon-free, because of the changes we've made to the Earth's climate in the past, the climate system will continue to warm. So we've actually already committed ourselves to certain climate warming no matter what we do. This is actually a fairly mild increase. And again, this is in degrees Celsius relative to the present day. So for those of you who are not comfortable with this, multiply by 2 to get Fahrenheit. And we're starting off with just to put this range of CO2 in concentration, this high value, which is sort of a very fossil fuel intensive scenario, represents a tripling of carbon dioxide relative to its pre-industrial levels. There's no value of carbon dioxide this high in the last million years. In fact, if we go this route, we'll be at a level of CO2 which the Earth hasn't experienced in the last 20 million years. So before even the advent of our very primitive ancestors, this is a historically unprecedented level of carbon dioxide. As is the medium scenario, the low value is something that we might be able to attain. I must admit, though, it is above the level that Europeans regard as dangerous. So depending on what scenario we follow, you can see that the higher the CO2 concentration, the higher the temperature at the end of the 21st century. Very simple. The more CO2 you emit, the warmer it's going to get. And the global temperatures can increase by anywhere between 1.5 to 3 degrees Kelvin, or between about 3 to 6 degrees Fahrenheit. What does this look like on a map? So in the near term, this is the year 2020, and this is the year basically 2100. So by 2020, the Earth will warm up a little bit. And one of the conclusions we reached is that, again, because of the inertia in the climate system, this is sort of warming that we're already committed to. We're not going to be able to dodge this warming. It's not incredibly bad. Over the continental United States, it's on the order of about 1 to 1.5 degrees centigrade, or about 2 to 3 degrees Fahrenheit. That actually makes the problem a little bit simpler for people who are trying to adapt, look at the impacts of climate change and adapt our urban infrastructure to handle climate change. It means that it's quite predictable. So that's actually a good sort of a silver lining. The bad news is that by the end of the century, it really does make a difference what we do. And the climate change at high latitudes is extraordinarily large. It's 6 degrees centigrade. What this means is that the permafrost will have melted for meters down below the surface. And all of northern Russia will be completely different. Alaska will have a completely different climate. The Arctic will have a completely different climate. So let's talk about the Arctic for a moment. This is a movie of the thickness of sea ice over the Arctic from our climate model. And we're sort of advancing through the 21st century. Blue means there's no sea ice. So by the latter part of the century, there is no more sea ice in the Arctic. And some people view this as I guess, as a business opportunity. And I think somewhat, they actually are interested in drilling for oil on the bottom of the Arctic. And Denmark, for example, is in the process of trying to figure out whether its continental shelf extends as far as Greenland, because that means that under international law it gets to claim the oil rights on that continental shelf all the way from Denmark to Greenland. So there's going to be quite a lot of activity in the Arctic in the near future. There was just an article in Harper's about how the Canadians are getting ready to seize their part of the Arctic. And there's already been discussions about who owns what part of the ocean up there. Setting aside people's business interests, there's going to be a dramatic decrease in the amount of sea ice. Again, the decrease increases with increasing carbon dioxide. So the more CO2 you emit, the more ice you eliminate. And this is going to have drastic consequences for all the ecosystems around the Arctic and plants and animals that depend on the ice for their survival. One other change that I want to talk about a little is the change in precipitation. This obviously is a change that's very important to us here in California. This graph is very busy, but what it basically says is that the storm tracks, which I mentioned at the beginning of my talk when I was pointing out the cloud distributions, the storm tracks are going to shift northward in both hemispheres. So the storms will move up toward Alaska, up toward Washington State and Canada in the northern hemisphere. The storm tracks will move south in the southern hemisphere, and the tropics are going to get drier. And this is the storm track movement, by the way, is something that we think we may have already seen in satellite observations. So this is already beginning to manifest itself. I'll come back to the implications for California in just a moment, but let's focus in a little bit on the United States and ask what do these changes mean for our country. This movement in storm tracks means that if you look at the incidents, for example, of periods when it's really dry, those get more frequent over the contiguous United States, and they certainly become more frequent. I know you can't read the scale, but the scale runs from, the red color corresponds to an increase of about a week and a half of periods when there's less than a millimeter of rain. So they're going to be very long stretches, up to 2 weeks, that that are sort of added to very dry periods in the western United States. And disturbingly, in the southeastern United States, those will increase by about a week or so. And it sort of doesn't really matter whether you're looking at low, medium, or high emissions. Of course, the Southeast right now is experiencing a level of drought that's reached critical levels, so within 90 days of running out of reservoir capacity in Georgia. The silver lining that everyone likes to talk about is longer growing seasons, and I realize this scale is not readable, so there are prospects for increasing growing seasons by up to about a month and a half because there'll be less frost. So this is one of the few silver linings for the United States from climate change. It'll be possible perhaps to grow 2 crop rotations in cases where those only possible to grow 1. And certainly this will help the agricultural field. Well, yeah, I'll show you what happens to California in just a moment. But this is one of the few silver linings, and actually the second assessment report looks at silver linings associated with climate change. This is one of the 2 silver linings. The other one is that there's a decreased incidence of colds. Those are the 2 benefits from global warming. The downside of having longer growing seasons is that we're going to be faced with much more severe heat waves. This scale runs up to 2 months. So the point of this graph, we called this, when we developed this, we instrumented the computer models this last time to look at what we called extreme conditions. And these are heat waves. This is a period of 5 days when it's more than 5 degrees centigrade or more than nearly 9 degrees Fahrenheit warmer than normal. We're now looking at the end of the century at periods when there are 2 months extra heat waves. Essentially, the extreme becomes the norm by the end of the 21st century. We're looking at summers that are incredibly hot, and they're incredibly hot every year. So the extreme, what we would regard as extreme now, becomes the norm by the end of the 21st century. Let's zoom in one step further to California and ask what happens to its water supply. And I'll skip this slide to focus on the snowpack. By the middle of the century, snowpack will have decreased by anywhere, by somewhere in the range of 25 to 40%. By the end of the century, even under the best scenario, you've eliminated 3/4 of the snowpack. And under the higher emissions scenarios, you've eliminated 90% of it. So we're going to have to figure out a different way of getting water in California. And by the way, this middle period corresponds to a period when by 2050, the estimates are that California will go from its current population of 36 million to 60 million people who are going to need water. So where is it going to come from? So this is the challenge that we face. And as I pointed out, this was kind of this is the end of at least the gloom. I'm not calling it doom, but I am calling it gloom. So let's talk about what we ought to have shown you. we are definitely changing the chemistry of the Earth's atmosphere. We think we can prove that we, mankind, are responsible for this. We think it is now very likely that the changes that we've seen in the recent past are due to this change that we have imposed on the chemical composition of the Earth's atmosphere. We're certain that the climate is warming and that this climate change will continue for centuries. So we've sort of put ourselves in a spot. How do we get out of it? Well, I want to point out that there's actually excellent precedent in the recent past for dealing with severe climate change. And the climate change I want to talk to you about is the ozone hole. This is a movie of the formation of the ozone hole setting up in 2004 over Antarctica from satellite. Satellites started taking measurements of the ozone concentration back in the late 1970s. And the satellite was actually, the software was set up so that it didn't believe the ozone hole when it first detected it. It literally threw it out because it thought it was an anomaly. And then they went back and corrected the software, and lo and behold, the ozone hole popped out. And it was because they were taking balloon measurements that were inconsistent with the satellites, and they thought, well, which one's right? And they realized the satellite software was wrong. They went back and corrected it, and here's our time record going from the 1970s up to the present day, almost the present day, of the formation of the ozone hole. And this is in units of the total amount of ozone in the columns extending from the Earth's surface up to the top of the atmosphere. And this purple color corresponds to a depletion of ozone over Antarctica. I don't know if you can see it, but this is the continent of Antarctica sitting right in the middle of the ozone hole. And the concentration of ozone decreased steadily from the 1960s up to the present day. So why is this bad? Well, ozone protects us from ultraviolet radiation. It's rather critical for the survival of life on Earth that we have ozone. And it was rapidly discovered, and there was a Nobel Prize given for this several years ago, why the ozone was decreasing. It's because we introduced a refrigerant called chlorofluorocarbons. These are chemicals that are chemically inert in the lower Earth atmosphere. They were a great replacement for ammonia, which we used to use in refrigerators. You can imagine having an ammonia leak in your kitchen. So CFCs were a great replacement for that. They didn't react with anything in the lower Earth atmosphere. Unfortunately, they act as a catalyst for ozone destruction, which means that the same molecule of chlorofluorocarbon can destroy thousands of molecules of ozone. And once people realized that this was happening, obviously this was a major challenge for the survival of life on Earth. Major challenge, what happened? The countries of the world came together and signed the Montreal Protocol in the 1980s. And that protocol is the member states have continued to meet to uphold that protocol. This is actually a recent photograph, a meeting of the Montreal members. And thanks to the advent of this protocol, which has basically put CFCs on a path to being phased out completely, the ozone hole is projected to basically recover by the middle of the 21st century. And this is I think, beg pardon?
When will it be covered?
By about the year 2065, according to current estimates. The point of this is that here's a major environmental challenge where the science was finally accepted by the international community, and the international community met, took action, and the problem is on its way to being solved. So, huge success story. I think this can be replicated for global warming. And we're very fortunate to live in a state which is leading the country in terms of action. This is the signing ceremony for a bill called AB 32, which has committed the state to reducing its emissions of carbon dioxide. This is a time series going from present day up to the year 2020 in terms of the total emissions of carbon dioxide from California. California is committing itself to rolling its emissions in the year 2020 back to their value at the year 1990. So in 2020, we'll have gone up a little, we'll sort of go up for a little bit, and then we'll come back down to 1990. And the governor has committed us, at least in principle, to much more aggressive cuts beyond that. So California is leading the country now in terms of its actions to address climate change. And if California can do it, so can the rest of the country. Lawrence Berkeley Lab is working very hard now on a variety of areas with regards to climate change science. And the area that I'm leading is associated with building more advanced models that we can use to predict climate change, but not only to predict it, but to link it to policy action. The models that I've shown you were designed primarily as scientific tools, so they don't really have the interactions with plants, animals, and human society built into them. So we can't look at what happens, for example, if we introduce a biofuel, how does that improve climate change or reduce global warming out into the future? We're now in the process of constructing those models, and also, thanks to the laboratories initiative, building major new computational facilities, which will be coming online in the next few years. This is an artist rendering of a building that's being added to the Lawrence Berkeley Lab. It's a computational research and theory facility, which will house some of the most advanced computers on Earth, which we will use to develop and then apply new climate models that include all the science bit that I've been describing to you, but also a feedback loop where we include people. And we allow people and their actions to mitigate climate change to feed back on climate change. This is where we're going in the future. And thanks to the lab, we'll have the facilities that are required to take that kind of action. So I'm actually an optimist at heart about all this. We also, fortunately, due to work over the last 30 years, have a lot of technology in hand and are actively developing technology to move to either more carbon neutral or carbon free sources of energy. This is a rendering of a windmill farm. They're now converting oil derricks in the Gulf to windmill farms, which I think is a perfect use for an oil platform. This is a picture of switchgrass, which, maybe not switchgrass, but another type of grass that grows very rapidly, doesn't require nitrogen fertilizers, and can be converted to biofuels. And the lab and a lot of other partners in California are now actively exploring using biofeedstock to substitute for petroleum, generate forms of energy that are carbon neutral. And of course, there's solar, and the lab is now exploring new types of solar cells that are far more efficient than the current ones that we have available. So we've sort of been going from global action to state action to local action, and I would like to conclude with Berkeley and companies closer to home, San Francisco. So here's our mayor, who has formed a climate action team and is looking very actively at reducing Berkeley's own contribution to global warming, and is obviously putting his money where his mouth is by driving very clean vehicles. San Francisco has a Bike to Work Day, and this is a picture taken from the 2007 Bike to Work Day from obviously the Golden Gate Bridge. And we have companies in California, just south of us, that are developing very advanced completely electric automobiles. I wish I could afford this one. The Tesla is a spectacular all-electric car, and the genius behind it is that it's based on the same battery technology that's used in laptops. So they've exploited the fact that computer companies and cell phone companies have been driving battery technology as hard as they possibly can to increase the power density, and they've utilized that technology to build a truly amazing automobile, which is very expensive right now, but it's obviously a first of its kind. And so I think there's reason to be optimistic that we can move toward a far more environmentally sustainable future. And with that, I would like to close and take your questions. Thank you very much. Yes.
We're going to have Timothy Burrows.
That's right. Actually, I think we're going to have a speaker just before we take questions.
Right. If I could just speak for a minute.
Sure.
I'd like to introduce Timothy Burrows. As Bill Collins referenced, the Berkeley voters passed Measure G in November 2006 to develop a plan to reduce greenhouse gases. So I'd like to hear from Timothy Burrows about what that is all about, and tell us about Berkeley's efforts to develop a plan for climate change.
Thank you very much. Thanks for having me here today. I really enjoyed the presentation, and I look forward to the questions, and I actually have a few questions too. Thanks for having me here today. My role at the City of Berkeley is as Climate Action Coordinator, and the City of Berkeley is one of the few cities in the country that actually has somebody called that, a Climate Action Coordinator. So we should, for those of you that are Berkeley residents, you should be proud that that your city is really moving to take aggressive action on greenhouse gas emissions. And for those of you that aren't Berkeley residents, make sure that when you go back to your city, you tell your city council members and your mayor that they should be doing it too. But a lot of the cities around the Bay Area are really taking aggressive action right now. As Bill mentioned, and Terry, last November, 81% of Berkeley residents voted for ballot Measure G. And what Measure G did is it established a greenhouse gas emissions reduction target for our community-wide emissions. And that target is an 80% reduction below 2000 levels by the year 2050. It's a very aggressive target, similar to the target established by AB 32 at the state level. And Measure G also directed the city to develop a plan for achieving that target. So it's clear that most of us in Berkeley, 81% of us, really believe that we should be taking aggressive action on this issue locally. It's not clear that we all agree on what that action should be. And so what we're doing right now is we are developing a plan that takes into account the ideas and the suggestions of community members, residents, business owners, city staff, everyone in the community. We're developing a plan that really can serve as a blueprint for achieving that 80% reduction by 2050. And 80% is not going to be easy, but I'm optimistic that it's possible. And our planning process really started with identifying where our emissions come from. So in Berkeley, we know now that most of our emissions come from transportation. About 50% of Berkeley's greenhouse gas emissions come from the cars we drive. You know, our trips to the store, our trips to drop our kids off at soccer practice, our commute to work. 50% of our emissions come from driving vehicles within the city of Berkeley. And basically, a rough estimate is about the other half come from the energy, the electricity and the natural gas we consume in our homes, in our businesses, in our institutions like our schools, our city government, our libraries, and so on. So we know where our emissions come from. We know that we want to reduce those emissions. We have a target to reduce those emissions. And we ultimately know that local governments, communities like Berkeley, but not only Berkeley, are really uniquely capable of addressing the main sources of greenhouse gas emissions. We can do something about how people get around our community through land use decisions, for example. We can do something about how much energy we consume in our homes through regulations and incentives and public education. And we can do something about how much energy is consumed in our businesses through similar means, regulations and incentives and outreach and education. So we're really, as a community, uniquely capable of addressing the causes of climate change and hopefully averting some of the scarier impacts that Bill was outlining for us. There's a couple of things that we know we have to do. We know in Berkeley, if we're going to hit 80%, we have to aggressively increase energy efficiency in our homes and in our businesses and in our city government everywhere. We also have to shift to decentralized sources of renewable energy like solar and like wind. And as we just heard, that technology is available. We just have to make the decision to switch to it. And the city government's role is to make it easier for residents and business owners to make that switch. We also have to make it easier for people to get around without driving their car through land use decisions, through bicycle and pedestrian infrastructure, so making people feel safer to get around on their bikes. And if we do have to drive, we have to make sure we drive fuel-efficient vehicles. Recycling, composting, reusing things is also a big thing we know we have to do in our community to achieve greenhouse gas emissions reductions. And like I said, all of those things are things we can do, things that we're uniquely capable of doing as a community, as the city of Berkeley. So I'm going to end now, but what can you do to be a part of this effort in Berkeley? One is, as you walked in, you might have seen this big poster with a bunch of people that have put their signature there. That's a little thing we created to try to engage individuals in Berkeley to reduce greenhouse gas emissions in their own homes. If we're going to achieve 80%, then everybody's going to have to do something. Really, nobody can slack. It's got to be residents, business owners, city staff, city elected officials, everybody have to do something. And one way to start is to just make a commitment. Commit by signing that pledge that you're going to do something. And once you make that commitment, there's a lot of help out there that can help you figure out what it is that you can do. There's a yellow piece of paper out there that has a bunch of different ideas on it for things you can do. One good idea is just doing a real quick energy audit in your home. An energy audit, a water audit. Try to identify where you're wasting energy, where you're wasting water. Look at your transportation habits. Where can you cut a trip out, a vehicle trip out, and go by bike or by foot instead? There's a lot of things that we can do. And as an individual, if I do less, if I emit less emissions, it's not going to make a big difference. But if we all do it, it will make a big difference. So we're part of the problem, but we can also very much be part of the solution. And I think I'll turn it back over to Bill. Thanks for having me here tonight again.
Microphones on either aisle. If you would come after the microphone to ask the questions, I think they raise the lights.
Hi, my name is Daniel. Thank you for your talk. You seem to be quite proud of the fact that the UN climate group got a unanimous agreement on certain things, but doesn't that also mean that it really was the lowest common denominator, and that it's actually going to be far worse than what this group that everyone would agree on would say? And has it been true that the recent events, like the melting of the ice, actually been far worse than the predictions have been?
No, not exactly. I mean, this is not an issue where I want to be clear that the governments didn't get to vote on whether or not we made certain statements in the report. In other words, what we did was we handed them a report and said, you can edit the punctuation, but the report that we submitted to them went through 95% unchanged. And I'm talking about now at the level of adding, white space. So the governments had very little influence on our findings. I think the issue that you're raising is that the IPCC is an assessment of research. And it's research, and this is a snapshot that we're taking periodically. So there's always some latest and greatest finding that's out there that says things are much worse. And to be honest with you, that may be true or it may not be, but it has not gone through adequate peer review and assessment by a broader community. In other words, scientists like to check everything from a lot of different angles. And so one of the recent statements that was made about the IPCC is that it grossly underestimated sea level rise. Well, that may or may not be true. This is a single scientist's assertion. And what we need to do now in the next 6 years is to go back and look very carefully at the evidence, and maybe that finding will hold up. And if it does, great, we'll report it in the next finding. I think what you're looking at, you should look at this as basically being just, it's like a strobe light that's being flashed on the science, and the scientific process, will right itself. But this is not a situation where, let me turn the question around. I mean, we could put in people's speculation about the worst possible scenarios, but that actually is not, many of those findings are not adequately supported by a large enough body of literature that I think they're scientifically defensible. And so, sure, this may be the floor on which we may see much more severe climate change. But I think that actually makes it, in some sense, more useful. We're not saying we're not making a claim about the sky is falling, right? We're simply saying that this is what all the scientists can agree on.
Okay, but I was going to say, but isn't this a little different, though, than other scientific subjects, because sort of time is of the essence as well?
Oh, sure. And believe me, having just committed 3 years of my life to this, we're working on this as fast as we can, but we can't put in to the report findings that are sort of, fresh, hot off the press, which have not been adequately validated. Because we're now asking the entire world to agree that this particular finding is, should be recognized as the state of the science, and it may not be. It may be just a flash in the pan.
So at one point you mentioned that this is the highest CO2 levels that the Earth has seen in millions of years.
Mm-hmm.
So if millions of years ago the CO2 levels were that high, is basically life pulling CO2 out of the climate and putting it into these fossil fuels that we're now burning? So we kind of resetting the clock back to some level, and can we look back and see what climate was like back then?
Well, it was a lot warmer, right? And you can go into the fossil record and find evidence for alligators living up at the latitude of Alaska. So, yes, it's been much hotter in the past. And there are a variety of processes that take CO2 out of the climate and stick it into the ground, sort of sequester it from contact with the atmosphere. Forming, mineral deposits include carbon dioxide that's been sort of removed from the climate system. The ocean draws down carbon dioxide and ends up depositing it on the ocean floor, where it can be turned into mineral deposits. The perverse thing that we're doing is we're going back and taking carbon dioxide that's sort of been safely out of the climate system because it was in geologic formations and dumping it back in. And that's not a very smart thing to do.
Your research is fascinating, and I hope you show us again. I'm concerned that trees are being removed, and they take the carbon out of the atmosphere, and if you cut them down, one mature tree, the figure is 3 tons of carbon go back in. So, as good research as you are doing in Lawrence Berkeley Labs, the cutting of the trees, and the 15 labs that you want to put in that green belt, we have 2 parks, and then the area that you will be deforesting and building all those bare buildings. Okay, I think that's criminal, and you should not be doing it there. You need to find another place. And another thing is I read recently that the university wants to take out the eucalyptus, which we knew were a problem. But you don't come in with what we got going on the earth, and you wipe out 23,000. That's what they want, 23,000 eucalyptus. We've got to figure a slower process because with the global warming, the new trees that you plant won't grow back.
So I think,
And thank you.
Sure.
I would like you to consider that while you pave over the earth, you're destroying the thing that is the best thing we got going, and it's happening all over with your switchgrass in other third world countries. Isn't it a terrible thing to be growing that and then shipping it over here? We've got to stop and start doing things right and save our trees.
Thank you. So I think the issue that the question was raising is, she was specifically referring to Lawrence Berkeley Labs, but we have looked seriously at the issue of the effects of deforestation and have tried to quantify that. And it turns out that it is adding a small amount, a very small amount, much less than carbon dioxide combustion, to global warming. It's down by a factor of about 20 compared to fossil fuel combustion. Most of the deforestation that's affecting the Earth's climate right now is happening in the tropics, actually, not at mid-latitudes. The biggest concern that we face right now is not so much deforestation, it's that when you heat land surfaces up, they may stop acting as sinks of carbon dioxide and turn into sources. And so the issue is really not so much deforestation. I mean, it's an important one. No, it's not quantitatively, it's not. The issue is primarily heating land surfaces, which once you do that, and we'll get there by the end of the 21st century, land may actually start outgassing CO2 rather than acting as a net sink of it, which would be unfortunate. That's still in sort of the unproven science claim area.
Trees cool the earth.
So, next question.
I have 2 questions. First is, you mentioned, when you gave the analogy with the moon, that we do have a major greenhouse gas effect, warming goal, which is due to water vapor, and the CO2 acts sort of as an amplifier. I wonder if you could comment on that a little bit. The second is, there's been some recent speculation that you could reduce the CO2 in the atmosphere or reduce the sunlight by putting mirrors in orbit.
So you were asking sort of two questions. The first is, what causes the greenhouse effect naturally? Water vapor turns out to be the primary greenhouse gas in the Earth's atmosphere. About 60% of the greenhouse effect is due to water vapor, and then about nearly 30% is due to CO2. So CO2 is the second most important greenhouse gas. Water vapor is the most important. There are prospects for potentially removing CO2 at its source when it's combusted. There's been quite a lot of work done on figuring out how to sort of sequester CO2 at the point of combustion. For example, if you continue to use fossil fuels or other types of fuel that require the production of CO2. The other part of your question dealt with what's known as geoengineering, which is the idea of sort of not addressing the greenhouse issue directly, but instead trying to offset it by reducing the amount of sunlight coming into the earth. And there have been two ideas that have been floated on this. One of them is to put a shield. Well, the people at Lawrence Livermore, once they got done with what they normally do, they sort of turned to something else, and they thought about putting up mirrors in the upper atmosphere. So that was called brilliant pebbles. And then there's been some discussion about putting a mylar shield in the same place where the SOHO satellite sits, so it's parked between the Earth and the sun. And then there's been discussion about flooding the stratosphere with sulfate aerosol, so creating sort of a permanent volcano. All of those, I think, are far more complicated and represent a far higher risk of failure than dealing with the problem directly. I think it's sort of basically, rather than dealing with the issue of finding a sensible, sustainable, carbon-free energy source, sort of creating some sort of whiz-bang technical solution, which, I mean, I don't think it's very smart to, we've run one experiment on the climate system already, let's not run a second one. So, next question.
I understand that we're at about 380 or 385
Right.
parts per million carbon dioxide in the atmosphere, and I've heard James Hansen say that 450 parts per million is sort of the point at which we some tipping points start coming into play. I wonder if you could talk a little bit about that concept of a tipping point. What some of those tipping points might be, just sort of extrapolate a little bit on what happened. I mean, I know 450 is probably not a magic number where
it's not
collapses when we get there, but why that number, and what are some of the tipping points that might occur?
So this question refers to parts of the climate system that might abruptly change. And we're actually going to get funding now to look at this issue at the laboratory. There may be aspects of the climate system that can change very rapidly, even in response to a fairly small change in carbon dioxide. One of the tipping points that people are looking at now is whether or not Greenland could be put into a state where it will begin irreversibly melting. And if it does melt, it will take over 1,000 years to do so. But if it does melt, that corresponds to 8 meters or over 24 feet of sea level rise. So we're talking about a fairly dramatic change in the coastlines of most of the countries in the world. And about half the people in the United States live within I think less than 30 miles of the coast. So this will have big effects all over. Another tipping point that is of concern is the prospect for, it was actually shown in the movie The Day After Tomorrow, somehow putting the ocean into a different state, where, for example, you get rid of the Gulf Stream. We've looked at that quite a bit in the IPCC report, and we couldn't drive the climate hard enough to make the Gulf Stream go away. We can make it weaken, but we couldn't make it go away. So I think The Day After Tomorrow is probably, that particular tipping point is probably an exaggeration. The others that, let's see, let me think of the other ones that come to mind. I mean, these are all, I think the challenge for us, just let me phrase this in terms of how scientists look at this problem. We've had a very stable climate for the last 10,000 years, and we've built our climate models based on what we've seen in the observational record. We're now taking the climate models sort of outside their comfort zone. So we're now trying to extrapolate based on physics and chemistry. The other tipping points that look unpleasant are, there's a lot of methane trapped in frozen form in the ocean floor. Methane is also a greenhouse gas. There's a lot of it in the Arctic. And we think we may heat up the Arctic to the point where we will let that methane melt. So it'll sort of act as a positive feedback on global warming. That, according to the projections I've seen, could easily happen this century. There's also this issue I mentioned earlier about the land sort of going from a sink to a source of carbon dioxide. And the one that just came out in this report that will be looked at quite a bit over the next 6 years is the issue of ocean acidification. This is not so much a tipping, well, it could be considered a tipping point. A lot of the single-celled organisms in the ocean that form the base of the food chain use calcium compounds to form their exoskeletons. So they're like ants. They have a hard shell on the outside. And those shells will dissolve if you lower the pH of ocean water. And in fact, that's exactly what we're doing by adding carbon dioxide. If you take a flask of seawater and you put carbon dioxide into it and you shake it, you can watch the microorganisms dissolve. So there's some concern now about the impact on the ocean, on the food chain from carbon dioxide. So I think, the bottom line here is not to, let me just summarize, and that's a lot of phenomena that may or may not occur. Scientists have looked very hard at the issue of whether or not there is any silver lining to global warming. And the only two things we were able to find are fewer colds. So I know some pharmaceutical companies are probably concerned about this. And longer growing season. And the rest of it just does not look good. I think it's a serious problem that we have to address. Next question.
And use wind and solar, that will go away.
Precisely.
So what is the ramification of that? Do we have enough data?
Mm-hmm.
An underlying theme to that is, of course, China is adding
Mm-hmm.
sufficient coal to, it equals the UK grid per year, which is astonishing. So is that even a realistic thing?
It is, and let me rephrase, if I may, just slightly rephrase or recast your question. So, if you remember that graph where I was showing you, there were bars that were red that showed heating, and then there were bars that were cool that showed cooling, and they all added up to a net heating effect. And the question regards what happens if you took away the cooling effect, what would happen? Well, that actually is, to a certain extent, a realistic prospect. The reason is that greenhouse gases last for a long time in the Earth's atmosphere. Carbon dioxide has a mean lifetime of over a century. The chlorofluorocarbons have lifetimes measured in tens of thousands of years. So they're going to be here for a long time. The aerosol, so those are the things that heat. The things that heat are around for a long time. The things that cool have a lifetime in the troposphere of about a week. They can be rained out. And the only reason why they're there all the time is that we're constantly emitting them. We're constantly burning coal. So as you move to, this is the sort of the, unfortunately, the double-edged sword aspect of air quality. As you move to better air quality, lower particulates, you actually exacerbate global warming. So people have run the experiment of asking what happens if you took out all the particulates in the Earth's atmosphere, and you basically double the amount of global warming we've seen since the start of industrialization. The planet would almost instantly heat by about 3/4 of a degree Celsius, so double the signal that we've seen. That said, that's sort of a near-term issue. As you move further and further out into the 21st century, because of air quality issues and other projected technology improvements, greenhouse gases dominate. And so by the end of the 21st century, you could take air quality measures without having any effect on global warming because greenhouse gases are going to totally dominate what's happening. But it is an important issue and one that we're actually now funded to look at. Yes?
Yes, I have a question on production of carbon dioxide is burning of coal and carbon
Mm-hmm.
that takes oxygen. Is there any concern about the oxygen that we use in the atmosphere to produce all this carbon dioxide?
Excellent question. That's actually one of the chemical lines of evidence that we have for the fact that it is fossil fuel combustion, because we can measure the decrease in the amount of oxygen now, and it tracks perfectly with the production of CO2 from fossil fuel combustion. So it's a direct chemical signature. Those changes are down, everybody should not sort of run out and run to an oxygen bar right this minute. These decreases are measured at the level of hundreds of parts per million at best, and we have 200,000 parts per million of oxygen in the Earth's atmosphere. So far, there's a
fact that there's parts per million, 21% oxygen, larger amount of oxygen.
Yeah, even under the most insane fossil fuel combustion scenarios, I think we're going to be okay. Something else will get us before the oxygen.
I think we should have the last question.
Sure.
I'd like to go back to Greenland for a minute. It's, you keep hearing things how it's melting faster than people anticipated, and you hear stories about how carbon dioxide is up in the atmosphere for 2 or 3 centuries at least, and you look at the rate of increase, and we're going to probably blow past 450 in some parts per million.
Oh, yeah.
What is the physical science that gives us any confidence that we're not on a path now of melting Greenland, period?
Could you repeat the question?
The question is, how do we know that we have not set Greenland on a permanent path to being melted? And Greenland is obviously getting some amount of it's being replenished by snowfall every year. So if you look at Antarctica, for example, just to take a different large ice sheet, it's actually not clear if Antarctica is decreasing because there's so much additional snowfall over the central part of Antarctica that the net mass balance may be close to zero. Greenland is our understanding of Greenland is still rudimentary. This is something I've been talking to people about quite a bit here. One of the reasons why Greenland is challenging, the reason why I'm not going to give you a direct answer to your question, is that the decrease in the amount of ice in Greenland appears to be more of a dynamic phenomenon than a thermodynamic phenomenon, just melting. And we do not understand the dynamics of the Greenland ice sheet well enough to be able to make accurate projections. This is something the community is working very hard on. But I would be remiss if I gave you a definitive answer about when we might send Greenland into a state of permanent melting. The rudimentary models that we have that I mentioned earlier do show that, becoming more likely by the mid-century. But those models are quite rudimentary.